Steel or aluminum can be shaped by pushing the metal back and forth between the wheels. Very little pressure is needed to shape the panel, which is stretched or raised to the desired shape. It is important to work slowly and gradually curve the metal into the desired shape. Monitor the curvature with frequent references to the template. The English wheel is used for shaping low crowns on large panels and polishing or planishing. To smooth the surface of a metal by rolling or hammering it, parts that have been formed with power hammers or hammer and shot bag. Piccolo Former. The Piccolo Former is used for cold forming and rolling sheet metal and other profile sections, extrusions. Figure 4.65. The position of the ram is adjustable in height by means of either a hand wheel or a foot pedal that permits control of the working pressure. Be sure to utilize the adjusting ring situated in the machine head to control the maximum working pressure. The forming tools are located in the moving ram and the lower tool holder. Depending on the variety of forming tools included, the operator can perform such procedures as forming edges, bending profiles, removing wrinkles, spot shrinking to remove buckles and dents, or expanding dome sheet metal. Available in either fiberglass, to prevent marring the surface, or steel, for working harder materials, faces, the tools are the quick change type. Shrinking and stretching tools. Shrinking tools. Shrinking dies repeatedly clamp down on the metal, then shift inward. Figure 4.66. This compresses the material between the dies, which actually slightly increases the thickness of the metal. Strain hardening takes place during this process, so it is best to set the working pressure high enough to complete the shape rather quickly. 8 passes could be considered excessive. Caution: avoid striking a die on the radius itself when forming a curved flange. This damages the metal and the radius and decreases the angle of bend. Stretching tools. Stretching dies repeatedly clamp down on the surface and then shift outward. This stretches the metal between the dies, which decreases the thickness in the stretched area. Striking the same point too many times weakens and eventually cracks the part. It is advantageous to deburr or even polish the edges of a flange that must undergo even moderate stretching to avoid crack formation. Forming flanges with existing holes causes the holes to distort and possibly crack or substantially weaken the flange. Manual foot-operated sheet metal shrinker. The manual foot-operated sheet metal shrinker operates very similarly to the Piccolo Former, though it only has 2 primary functions, shrinking and stretching. The only dies available are steel-faced and therefore tend to mar the surface of the metal. When used on aluminum, it is necessary to gently blend out the surface irregularities, primarily in the cladding, then treat and paint the part. Since this is a manual machine, it relies on leg power, as the operator repeatedly steps on the foot pedal. The more force is applied, the more stresses are concentrated at that single point. It yields a better part with a series of smaller stretches, or shrinks, than with a few intense ones. Squeezing the dies over the radius damages the metal and flattens out some of the bend. It may be useful to tape a thick piece of plastic or micarta to the opposite leg to shim the radius of the angle away from the clamping area of the dies. Note: watch the part change shape while slowly applying pressure. A number of small stretches works more effectively than one large one. If applying too much pressure, the metal has the tendency to buckle. End of page 4-26. Hand-operated shrinker and stretcher. The hand-operated shrinker and stretcher is similar to the manual foot-operated unit, except a handle is used to apply force to shrinking and stretching blocks. The dies are all metal and leave marks on aluminum that need to be blended out after the shrinking or stretching operation. Figure 4.67. Dollies and stakes. Sheet metal is often formed or finished, planished, over anvils, available in a variety of shapes and sizes, called dollies and stakes. These are used for forming small, odd-shaped parts, or for putting on finishing touches for which a large machine may not be suited. Dollies are meant to be held in the hand, whereas stakes are designed to be supported by a flat cast iron bench plate fastened to the workbench. Figure 4.68. Most stakes have machined, polished surfaces that have been hardened. Use of stakes to back up material when chiseling, or when using any similar cutting tool, defaces the surface of the stake and makes it useless for finish work. Hardwood form blocks. Hardwood form blocks can be constructed to duplicate practically any aircraft structural or non-structural part. The wooden block or form is shaped to the exact dimensions and contour of the part to be formed. V-blocks. V-blocks made of hardwood are widely used in airframe metalwork for shrinking and stretching metal, particularly angles and flanges. The size of the block depends on the work being done and on personal preference. Although any type of hardwood is suitable, maple and ash are recommended for best results when working with aluminum alloys. Shrinking blocks. A shrinking block consists of two metal blocks and some device for clamping them together. One block forms the base and the other is cut away to provide space where the crimped material can be hammered. The legs of the upper jaw clamp the material to the base block on each side of the crimp to prevent the material from creeping away, but remains stationary while the crimp is hammered flat, being shrunk. This type of crimping block is designed to be held in a bench vise. Shrinking blocks can be made to fit any specific need. The basic form and principle remain the same, even though the blocks may vary considerably in size and shape. Sandbags. A sandbag is generally used as a support during the bumping process. A serviceable bag can be made by sewing heavy canvas or soft leather to form a bag of the desired size, and filling it with sand which has been sifted through a fine mesh screen. Before filling canvas bags with sand, use a brush to coat the inside of the bag with softened paraffin or beeswax, which forms a sealing layer and prevents the sand from working through the pores of the canvas. Bags can also be filled with shot as an alternative to sand. End of page 4 to 27. Sheet metal hammers and mallets. The sheet metal hammer and the mallet are metal fabrication hand tools used for bending and forming sheet metal without marring or indenting the metal. The hammer head is usually made of high-carbon, heat-treated steel, while the head of the mallet, which is usually larger than that of the hammer, is made of rubber, plastic, wood, or leather. In combination with a sandbag, V-blocks, and dies, sheet metal body hammers and mallets are used to form annealed metal. Figure 4:69. Sheet metal holding devices. In order to work with sheet metal during the fabrication process, the aviation technician uses a variety of holding devices, such as clamps, vices, and fasteners to hold the work together. The type of operation being performed and the type of metal being used determine what type of the holding device is needed. Clamps and vices. Clamps and vices hold materials in place when it is not possible to handle a tool and the workpiece at the same time. A clamp is a fastening device with movable jaws that has opposing, often adjustable, sides or parts. An essential fastening device, it holds objects tightly together to prevent movement or separation. Clamps can be either temporary or permanent. Temporary clamps, such as the carriage clamp, commonly called the C-clamp, are used to position components while fixing them together. C-clamps. The C-clamp is shaped like a large C and has three main parts: threaded screw, jaw, and swivel head. Figure 4:70. The swivel plate or flat end of the screw prevents the end from turning directly against the material being clamped. C-clamp size is measured by the dimension of the largest object the frame can accommodate with the screw fully extended. The distance from the center line of the screw to the inside edge of the frame or the depth of throat is also an important consideration when using this clamp. C-clamps vary in size from 2 inches upward. Since C-clamps can leave marks on aluminum, protect the aircraft covering with masking tape at the places where the C-clamp is used. Vices. Vices are another clamping device that hold the workpiece in place and allow work to be done on it with tools such as saws and drills. The vise consists of two fixed or adjustable jaws that are opened or closed by a screw or a lever. The size of a vise is measured by both the jaw width and the capacity of the vise when the jaws are fully open. Vices also depend on a screw to apply pressure, but their textured jaws enhance gripping ability beyond that of a clamp. Two of the most commonly used vices are the machinist's vise and the utility vise. Figure 4:71. The machinist's vise has flat jaws and usually a swivel base, whereas the utility bench vise has scored, removable jaws and an anvil-faced back jaw. This vise holds heavier material than the machinist's vise and also grips pipe or rod firmly. The back jaw can be used as an anvil if the work being done is light. To avoid marring metal in the vise jaws, add some type of padding, such as a ready-made rubber jaw pad. Reusable sheet metal fasteners. Reusable sheet metal fasteners temporarily hold drilled sheet metal parts accurately in position for riveting or drilling. If sheet metal parts are not held tightly together, they separate while being riveted or drilled. The Cleco, also spelled Cleco, fastener is the most commonly used sheet metal holder. Figure 4.72. End of page 4 to 28. Cleco fasteners. The Cleco fastener consists of a steel cylinder body with a plunger on the top, a spring, a pair of step-cut locks, and a spreader bar. These fasteners come in 6 different sizes: 3/32, 1/8, 5/32, 3/16, 1/4, and 3/8 inch in diameter with the size stamped on the fastener. Color coding allows for easy size recognition. A special type of plier fits the 6 different sizes. When installed correctly, the reusable Cleco fastener keeps the holes in the separate sheets aligned. Hex nut and wing nut temporary sheet fasteners. Hex nut and wing nut fasteners are used to temporarily fasten sheets of metal when higher clamp-up pressure is required. Figure 4.73. Hex nut fasteners provide up to 300 pounds of clamping force with the advantage of quick installation and removal with a hex nut runner. Wing nut sheet metal fasteners, characterized by wing-shaped protrusions, not only provide a consistent clamping force from 0 to 300 pounds, but the aircraft technician can turn and tighten these fasteners by hand. Cleco hex nut fasteners are identical to Cleco wing nut fasteners, but the Cleco hex nut can be used with pneumatic Cleco installers. Aluminum alloys. Aluminum alloys are the most frequently encountered type of sheet metal in aircraft repair. AC 43.13-1 Chapter 4, Metal Structure, Welding, and Brazing, Section 1, Identification of Metals, as revised, provides an in-depth discussion of all metal types. This section describes the aluminum alloys used in the forming processes discussed in the remainder of the chapter. In its pure state, aluminum is lightweight, lustrous, and corrosion resistant. The thermal conductivity of aluminum is very high. It is ductile, malleable, and non-magnetic. When combined with various percentages of other metals, generally copper, manganese, and magnesium, aluminum alloys that are used in aircraft construction are formed. Aluminum alloys are lightweight and strong. They do not possess the corrosion resistance of pure aluminum and are usually treated to prevent deterioration. Alclad aluminum is an aluminum alloy with a protective cladding of aluminum to improve its corrosion resistance. To provide a visual means for identifying the various grades of aluminum and aluminum alloys, aluminum stock is usually marked with symbols such as a government specification number, the temper or condition furnished, or the commercial code marking. Plate and sheet are usually marked with specification numbers or code markings in rows approximately 5 inches apart. Tubes, bars, rods, and extruded shapes are marked with specification numbers or code markings at intervals of 3 to 5 feet along the length of each piece. The commercial code marking consists of a number that identifies the particular composition of the alloy. End of page 4 to 29. Additionally, letter suffixes designate the basic temper designations in subdivisions of aluminum alloys. The aluminum and various aluminum alloys used in aircraft repair and construction are as follows. 1. Aluminum designated by the symbol 1100 is used where strength is not an important factor, but where weight economy and corrosion resistance are desired. This aluminum is used for fuel tanks, cowlings, and oil tanks. It is also used for repairing wingtips and tanks. This material is weldable. 2. Alloy 3003 is similar to 1100 and is generally used for the same purposes. It contains a small percentage of magnesium and is stronger and harder than 1100 aluminum. 3. Alloy 2014 is used for heavy-duty forgings, plates, extrusions for aircraft fittings, wheels, and major structural components. This alloy is often used for applications requiring high strength and hardness, as well as for service at elevated temperatures. 4. Alloy 2017 is used for rivets. This material is now in limited use. 5. Alloy 2024, with or without alclad coating, is used for aircraft structures, rivets, hardware, machine screw products, and other miscellaneous structural applications. In addition, this alloy is commonly used for heat-treated parts, airfoil and fuselage skins, extrusions, and fittings. 6. Alloy 2025 is used extensively for propeller blades. 7. Alloy 2219 is used for fuel tanks, aircraft skin, and structural components. This material has high fracture toughness and is readily weldable. Alloy 2219 is also highly resistant to stress corrosion cracking. 8. Alloy 5052 is used where good workability, very good corrosion resistance, high fatigue strength, weldability, and moderate static strength are desired. This alloy is used for fuel, hydraulic, and oil lines. 9. Alloy 5056 is used for making rivets and cable sheeting and in applications where aluminum comes into contact with magnesium alloys. Alloy 5056 is generally resistant to the most common forms of corrosion. 10. Cast aluminum alloys are used for cylinder heads, crankcases, fuel injectors, carburetors, and landing wheels. 11. Various alloys, including 3003, 5052, and 1100 aluminum, are hardened by cold working rather than by heat treatment. Other alloys, including 2017 and 2024, are hardened by heat treatment, cold working, or a combination of the two. Various casting alloys are hardened by heat treatment. 12. Alloy 6061 is generally weldable by all commercial procedures and methods. It also maintains acceptable toughness in many cryogenic applications. Alloy 6061 is easily extruded and is commonly used for hydraulic and pneumatic tubing. 13. Although higher in strength than 2024, alloy 7075 has a lower fracture toughness and is generally used in tension applications where fatigue is not critical. The T6 temper of 7075 should be avoided in corrosive environments. However, the T7351 temper of 7075 has excellent stress corrosion resistance and better fracture toughness than the T6 temper. The T76 temper is often used to improve the resistance of 7075 to exfoliate corrosion. Structural fasteners. Structural fasteners, used to join sheet metal structures securely, come in thousands of shapes and sizes, with many of them specialized and specific to certain aircraft. Since some structural fasteners are common to all aircraft, this section focuses on the more frequently used fasteners. For the purposes of this discussion, fasteners are divided into two main groups: solid shank rivets and special purpose fasteners that include blind rivets. Solid shank rivet. The solid shank rivet is the most common type of rivet used in aircraft construction. Used to join aircraft structures, solid shank rivets are one of the oldest and most reliable types of fastener. Widely used in the aircraft manufacturing industry, solid shank rivets are relatively low-cost, permanently installed fasteners. They are faster to install than bolts and nuts since they adapt well to automatic, high-speed installation tools. Rivets should not be used in thick materials or in tensile applications, as their tensile strengths are quite low relative to their shear strength. The longer the total grip length, the total thickness of sheets being joined, the more difficult it becomes to lock the rivet. Riveted joints are neither airtight nor watertight unless special seals or coatings are used. Since rivets are permanently installed, they must be removed by drilling them out, a laborious task. Description. Before installation, the rivet consists of a smooth cylindrical shaft with a factory head on one end. The opposite end is called the bucktail. To secure two or more pieces of sheet metal together, the rivet is placed into a hole cut just a bit larger in diameter than the rivet itself. Once placed in this pre-drilled hole, the bucktail is upset or deformed by any of several methods, from handheld hammers to pneumatically driven squeezing tools. End of page 4 to 30. This action causes the rivet to expand about 11/2 times the original shaft diameter, forming a second head that firmly holds the material in place. Rivet head shape. Solid rivets are available in several head shapes, but the universal, also known as protruding head, and the 100 degrees countersunk head are the most commonly used in aircraft structures. Universal head rivets were developed specifically for the aircraft industry and designed as a replacement for both the round and brazier head rivets. These rivets replaced all protruding head rivets and are used primarily where the protruding head has no aerodynamic significance. They have a flat area on the head, a head diameter twice the shank diameter, and a head height approximately 42.5% of the shank diameter. Figure 4.74. The countersunk head angle can vary from 60 degrees to 120 degrees, but the 100 degrees has been adopted as standard because this head style provides the best possible compromise between tension/shear strength and flushness requirements. This rivet is used where flushness is required because the rivet is flat-topped and undercut to allow the head to fit into a countersunk or dimpled hole. The countersunk rivet is primarily intended for use when aerodynamic smoothness is critical, such as on the external surface of a high-speed aircraft. Typically, rivets are fabricated from aluminum alloys, such as 2017 T4, 2024 T4, 2117 T4, 7050, and 5056. Titanium, nickel-based alloys, such as Monel, corrosion-resistant steel, mild steel or iron, and copper rivets are also used for rivets in certain cases. Rivets are available in a wide variety of alloys, head shapes, and sizes and have a wide variety of uses in aircraft structure. Rivets that are satisfactory for one part of the aircraft are often unsatisfactory for another part. Therefore, it is important that an aircraft technician know the strength and driving properties of the various types of rivets and how to identify them, as well as how to drive or install them. Solid rivets are classified by their head shape, by the material from which they are manufactured, and by their size. Identification codes used are derived from a combination of the Military Standard, MS, and National Aerospace Standard, NAS, systems, as well as an older classification system known as AN for Army/Navy. For example, the prefix MS identifies hardware that conforms to written military standards. A letter or letters following the head-shaped code identify the material or alloy from which the rivet was made. The alloy code is followed by two numbers separated by a dash. The first number is the numerator of a fraction, which specifies the shank diameter in 32nds of an inch. The second number is the numerator of a fraction in 16ths of an inch and identifies the length of the rivet. Rivet head shapes and their identifying code numbers are shown in Figure 4.75. The most frequently used repair rivet is the AD rivet because it can be installed in the received condition. Some rivet alloys, such as DD rivets, alloy 2024 T4, are too hard to drive in the received condition and must be annealed before they can be installed. Typically, these rivets are annealed and stored in a freezer to retard hardening, which has led to the nickname icebox rivets. They are removed from the freezer just prior to use. Most DD rivets have been replaced by E-type rivets which can be installed in the received condition. The head type, size, and strength required in a rivet are governed by such factors as the kind of forces present at the point riveted, the kind and thickness of the material to be riveted, and the location of the part on the aircraft. The type of head needed for a particular job is determined by where it is to be installed. Countersunk head rivets should be used where a smooth aerodynamic surface is required. Universal head rivets may be used in most other areas. The size, or diameter, of the selected rivet shank should correspond in general to the thickness of the material being riveted. If an excessively large rivet is used in a thin material, the force necessary to drive the rivet properly causes an undesirable bulging around the rivet head. On the other hand, if an excessively small rivet diameter is selected for thick material, the shear strength of the rivet is not great enough to carry the load of the joint. End of page 4-31. As a general rule, the rivet diameter should be at least 2.5 to 3 times the thickness of the thicker sheet. Rivets most commonly chosen in the assembly and repair of aircraft range from 3/32 inch to 3/8 inch in diameter. Ordinarily, rivets smaller than 3/32 inch in diameter are never used on any structural parts that carry stresses. The proper sized rivets to use for any repair can also be determined by referring to the rivets, used by the manufacturer, in the next parallel row inboard on the wing or forward on the fuselage. Another method of determining the size of rivets to be used is to multiply the skin's thickness by 3 and use the next larger size rivet corresponding to that figure. For example, if the skin is 0.040 inch thick, multiply 0.040 inch by 3 to get 0.120 inch and use the next larger size of rivet, 1/8 inch, 0.125 inch. When rivets are to pass completely through tubular members, select a rivet diameter equivalent to at least 1/8 the outside diameter of the tube. If one tube sleeves or fits over another, take the outside diameter of the outside tube and use 1/8 of that distance as the minimum rivet diameter. A good practice is to calculate the minimum rivet diameter and then use the next larger size rivet. Whenever possible, select rivets of the same alloy number as the material being riveted. For example, use 1100 and 3003 rivets on parts fabricated from 1100 and 3003 alloys, and 2117-1 and 2017 T rivets on parts fabricated from 2017 and 2024 alloys. The size of the formed head is the visual standard of a proper rivet installation. The minimum and maximum sizes, as well as the ideal size, are shown in Figure 4.76. Installation of rivets. Repair layout. Repair layout involves determining the number of rivets required, the proper size and style of rivets to be used, their material, temper, condition and strength, the size of the holes, the distances between the holes, and the distance between the holes and the edges of the patch. Distances are measured in terms of rivet diameter. Rivet length. To determine the total length of a rivet to be installed, the combined thickness of the materials to be joined must first be known. This measurement is known as the grip length. The total length of the rivet equals the grip length plus the amount of rivet shank needed to form a proper shop head. The properly formed shop head equals 1.5 times the diameter of the rivet shank. Where A is total rivet length, B is grip length, and C is the length of the material needed to form a shop head, this formula can be represented as A equals B plus C, Figure 4.76. Rivet strength. For structural applications, the strength of the replacement rivets is of primary importance. Figure 4.77. Replace rivets with those of the same size and strength whenever possible. If the rivet hole becomes enlarged, deformed, or otherwise damaged, drill or ream the hole for the next larger size rivet. However, make sure that the edge distance and spacing is not less than minimums listed in the next paragraph. Rivets may not be replaced by a type having lower strength properties, unless the lower strength is adequately compensated by an increase in size or a greater number of rivets. For example, it is acceptable to replace 2017 rivets of 3/16 inch diameter or less, and 2024 rivets of 5/32 inch diameter or less with 2117 rivets for general repairs, provided the replacement rivets are 1/32 inch greater in diameter than the rivets they replace. The 2117T rivet is used for general repair work, since it requires no heat treatment, is fairly soft and strong, and is highly corrosion resistant when used with most types of alloys. Always consult the maintenance manual for correct rivet type and material. The type of rivet head to select for a particular repair job can be determined by referring to the type used within the surrounding area by the manufacturer. End of page 4-32. A general rule to follow on a flush riveted aircraft is to apply flush rivets on the upper surface of the wing and stabilizers, on the lower leading edge back to the spar, and on the fuselage back to the high point of the wing. Use universal head rivets in all other surface areas. Whenever possible, select rivets of the same alloy number as the material being riveted. Stresses applied to rivets. Shear is one of the two stresses applied to rivets. The shear strength is the amount of force required to cut a rivet that holds two or more sheets of material together. If the rivet holds two parts, it is under single shear. If it holds three sheets or parts, it is under double shear. To determine the shear strength, the diameter of the rivet to be used must be found by multiplying the thickness of the skin material by 3. For example, a material thickness of 0.040 inch multiplied by 3 equals 0.120 inch. In this case, the rivet diameter selected would be 1/8, 0.125 inch. Tension is the other stress applied to rivets. The resistance to tension is called bearing strength and is the amount of tension required to pull a rivet through the edge of two sheets riveted together or to elongate the hole. Rivet spacing. Rivet spacing is measured between the center lines of rivets in the same row. The minimum spacing between protruding head rivets shall not be less than 31/2 times the rivet diameter. The minimum spacing between flush head rivets shall not be less than 4 times the diameter of the rivet. These dimensions may be used as the minimum spacing except when specified differently in a specific repair procedure or when replacing existing rivets. On most repairs, the general practice is to use the same rivet spacing in edge distance from the center of the hole to the edge of the material, that the manufacturer used in the area surrounding the damage. The SRM for the particular aircraft may also be consulted. Aside from this fundamental rule, there is no specific set of rules that governs spacing of rivets in all cases. However, there are certain minimum requirements that must be observed. 1. When possible, rivet edge distance, rivet spacing, and distance between rows should be the same as that of the original installation. 2. When new sections are to be added, the edge distance measured from the center of the rivet should never be less than 2 times the diameter of the shank, the distance between rivets or pitch should be at least 3 times the diameter, and the distance between rivet rows should never be less than 21/2 times the diameter. Figure 4.78 illustrates acceptable ways of laying out a rivet pattern for a repair. Edge distance. Edge distance, also called edge margin by some manufacturers, is the distance from the center of the first rivet to the edge of the sheet. It should not be less than 2 or more than 4 rivet diameters, and the recommended edge distance is about 21/2 rivet diameters. The minimum edge distance for universal rivets is 2 times the diameter of the rivet. The minimum edge distance for countersunk rivets is 21/2 times the diameter of the rivet. End of page 4-33. If rivets are placed too close to the edge of the sheet may crack or pull away from the rivets. If they are spaced too far from the edge, the sheet is likely to turn up at the edges. Figure 4.79. It is good practice to lay out the rivets a little further from the edge so that the rivet holes can be oversized without violating the edge distance minimums. Add 1/16 inch to the minimum edge distance or determine the edge distance using the next size of rivet diameter. 2 methods for obtaining edge distance. 1. The rivet diameter of a protruding head rivet is 3/32 inch. Multiply 2 times 3/32 inch to obtain the minimum edge distance, 3/16 inch, add 1/16 inch to yield the preferred edge distance of 1/4 inch. 2. The rivet diameter of a protruding head rivet is 3/32 inch. Select the next size of rivet, which is 1/8 inch. Calculate the edge distance by multiplying 2 times 1/8 inch to get 1/4 inch. Rivet pitch. Rivet pitch is the distance between the centers of neighboring rivets in the same row. The smallest allowable rivet pitch is 3 rivet diameters. The average rivet pitch usually ranges from 4 to 6 rivet diameters, although in some instances rivet pitch could be as large as 10 rivet diameters. Rivet spacing on parts that are subjected to bending moments is often closer to the minimum spacing to prevent buckling of the skin between the rivets. The minimum pitch also depends on the number of rows of rivets. 1 and 3 row layouts have a minimum pitch of 3 rivet diameters, a 2 row layout has a minimum pitch of 4 rivet diameters. The pitch for countersunk rivets is larger than for universal head rivets. If the rivet spacing is made at least 1/16 inch larger than the minimum, the rivet hole can be oversized without violating the minimum rivet spacing requirement. Figure 4.80. Transverse pitch. Transverse pitch is the perpendicular distance between rivet rows. It is usually 75% of the rivet pitch. The smallest allowable transverse pitch is 21/2 rivet diameters. The smallest allowable transverse pitch is 21/2 rivet diameters. Rivet pitch and transverse pitch often have the same dimension and are simply called rivet spacing. Rivet layout example. The general rules for rivet spacing, as it is applied to a straight row layout, are quite simple. In a 1-row layout, find the edge distance at each end of the row and then lay off the rivet pitch, distance between rivets, as shown in Figure 4.81. In a 2-row layout, lay off the first row, place the second row a distance equal to the transverse pitch from the first row, and then lay off rivet spots in the second row so that they fall midway between those in the first row. End of page 4-34. In the 3-row layout, first lay off the first and third rows, then use a straightedge to determine the second row rivet spots. When splicing a damaged tube, and the rivets pass completely through the tube, space the rivets 4 to 7 rivet diameters apart if adjacent rivets are at right angles to each other, and space them 5 to 7 rivet diameters apart if the rivets are parallel to each other. The first rivet on each side of the joint should be no less than 21/2 rivet diameters from the end of the sleeve. Rivet installation tools. The various tools needed in the normal course of driving and upsetting rivets include drills, reamers, rivet cutters or nippers, bucking bars, riveting hammers, draw sets, dimpling dies or other types of countersinking equipment, rivet guns, and squeeze riveters. C-clamps, vices, and other fasteners used to hold sheets together when riveting were discussed earlier in the chapter. Other tools and equipment needed in the installation of rivets are discussed in the following paragraphs. Hand tools. A variety of hand tools are used in the normal course of driving and upsetting rivets. They include rivet cutters, bucking bars, hand riveters, countersinks, and dimpling tools. Rivet cutter. The rivet cutter is used to trim rivets when rivets of the required length are unavailable. Figure 4.82. To use the rotary rivet cutter, insert the rivet in the correct hole, place the required number of shims under the rivet head, and squeeze the cutter as if it were a pair of pliers. Rotation of the discs cuts the rivet to give the right length, which is determined by the number of shims inserted under the head. When using a large rivet cutter, place it in a vise, insert the rivet in the proper hole, and cut by pulling the handle, which shears off the rivet. If regular rivet cutters are not available, diagonal cutting pliers can be used as a substitute cutter. Bucking bar. The bucking bar, sometimes called a dolly, bucking iron, or bucking block, is a heavy chunk of steel whose counter-vibration during installation contributes to proper rivet installation. They come in a variety of shapes and sizes, and their weights ranges from a few ounces to 8 or 10 pounds, depending upon the nature of the work. Bucking bars are most often made from low-carbon steel that has been case-hardened or alloy bar stock. Those made of better grades of steel last longer and require less reconditioning. Bucking faces must be hard enough to resist indentation and remain smooth, but not hard enough to shatter. Sometimes, the more complicated bars must be forged or built up by welding. The bar usually has a concave face to conform to the shape of the shop head to be made. When selecting a bucking bar, the first consideration is shape. Figure 4.83. If the bar does not have the correct shape, it deforms the rivet head. If the bar is too light, it does not give the necessary bucking weight, and the material may become bulged toward the shop head. If the bar is too heavy, its weight and the bucking force may cause the material to bulge away from the shop head. End of page 4 to 35. This tool is used by holding it against the shank end of a rivet while the shop head is being formed. Always hold the face of the bucking bar at right angles to the rivet shank. Failure to do so causes the rivet shank to bend with the first blows of the rivet gun and causes the material to become marred with the final blows. The bucker must hold the bucking bar in place until the rivet is completely driven. If the bucking bar is removed while the gun is in operation, the rivet set may be driven through the material. Allow the weight of the bucking bar to do most of the work and do not bear down too heavily on the shank of the rivet. The operator's hands merely guide the bar and supply the necessary tension and rebound action. Coordinated bucking allows the bucking bar to vibrate in unison with the gun set. With experience, a high degree of skill can be developed. Defective rivet heads can be caused by lack of proper vibrating action, the use of a bucking bar that is too light or too heavy, and failure to hold the bucking bar at right angles to the rivet. The bars must be kept clean, smooth, and well polished. Their edges should be slightly rounded to prevent marring the material surrounding the riveting operation. Hand rivet set. A hand rivet set is a tool equipped with a die for driving a particular type rivet. Rivet sets are available to fit every size and shape of rivet head. The ordinary set is made of 1/2 inch carbon tool steel about 6 inches in length and is knurled to prevent slipping in the hand. Only the face of the set is hardened and polished. Sets for universal rivets are recessed, or cupped, to fit the rivet head. In selecting the correct set, be sure it provides the proper clearance between the set and the sides of the rivet head and between the surfaces of the metal and the set. Flush or flat sets are used for countersunk and flathead rivets. To seat flush rivets properly, be sure that the flush sets are at least 1 inch in diameter. Special draw sets are used to draw up the sheets to eliminate any opening between them before the rivet is bucked. Each draw set has a hole 1/32 inch larger than the diameter of the rivet shank for which it is made. Occasionally, the draw set and rivet header are incorporated into one tool. The header part consists of a hole shallow enough for the set to expand the rivet and head when struck with a hammer. Countersinking tool. The countersink is a tool that cuts a cone-shaped depression around the rivet hole to allow the rivet to set flush with the surface of the skin. Countersinks are made with angles to correspond with the various angles of countersunk rivet heads. The standard countersink has a 100 degrees angle, as shown in Figure 4.84. Special micro-stop countersinks, commonly called stop countersinks, are available that can be adjusted to any desired depth and have cutters to allow interchangeable holes with various countersunk angles to be made. Figure 4.85. Some stop countersinks also have a micrometer set mechanism, in 0.001 inch increments, for adjusting their cutting depths. Dimpling dies. Dimpling is done with a male and female die, punch and die set. The male die has a guide the size of the rivet hole and with the same degree of countersink as the rivet. The female die has a hole with a corresponding degree of countersink into which the male guide fits. End of page 4 to 36. Power tools. The most common power tools used in riveting are the pneumatic rivet gun, rivet squeezers, and the micro shaver. Pneumatic rivet gun. The pneumatic rivet gun is the most common rivet upsetting tool used in airframe repair work. It is available in many sizes and types. Figure 4.86. The manufacturer's recommended capacity for each gun is usually stamped on the barrel. Pneumatic guns operate on air pressure of 90 to 100 pounds per square inch and are used in conjunction with interchangeable rivet sets. Each set is designed to fit the specific type of rivet and the location of the work. The shank of the set is designed to fit into the rivet gun. An air-driven hammer inside the barrel of the gun supplies force to buck the rivet. Slow-hitting rivet guns that strike from 900 to 2,500 blows per minute are the most common type. Figure 4.87. These blows are slow enough to be easily controlled and heavy enough to do the job. These guns are sized by the largest rivet size continuously driven with size often based on the Chicago Pneumatic Company's old X series. A 4X gun, -8 or 1/4 rivet, is used for normal work. The less powerful 3X gun is used for smaller rivets in thinner structure. 7X guns are used for large rivets in thicker structures. A rivet gun should upset a rivet in 1 to 3 seconds. With practice, an aircraft technician learns the length of time needed to hold down the trigger. A rivet gun with the correct header, rivet set, must be held snugly against the rivet head and perpendicular to the surface while a bucking bar of the proper weight is held against the opposite end. End of page 4 to 37.